Okay. The whole point of Friday's activity was to get you to start thinking about rules or functions that can take each input in a table and give you the output. So for each table, you should only have one function or one rule. So you can't have a rule for this line and a different rule for this line and a different rule. Like, you can't say add 9 for this line and add 15 and add 23. The rule has to be the same for each table. So if I were to look at this table right here, if I can't really find anything going from the input to the output, sometimes what I'll do is I'll look at the outputs and see if I can find a pattern in the outputs. So like on this one, I can see that this one is the same thing as 3 squared. This one is the same thing as 4 squared. This is the same thing as 5 squared, 6 squared, 7 squared. So what it looks like to me is that I'm going to be squaring something. And what that something is, I just have to figure out. So if I look at the difference between the input and what I'm squaring each time, so here I have 0, but I'm going to square 3. Here I have 1, but I'm going to square 4. Here I have 2, but I need to square 5. Here I have 3, but I'm going to square 6. Here I have 4, but I'm going to square 7. So for each one of these, if I add 3, that gives me what needs to be squared. So what I'm doing is I'm just taking the input, which is we usually call it our x value, and I'm adding 3 to it every time. And then I'm taking that whole value, not just the x and not just the 3, but I'm taking that whole value, that sum, and I'm squaring that. So if I take 0 plus 3, I do 3 squared, and that gives me 9. So 1 plus 3 is 4, 4 squared is 16, so on and so forth. So this rule is the same for each row in my input-output table. Okay. If I look at the next table, one of the things that we talked about today was that all of these are divisible by 5. So I need to multiply something by 5. 5 times something is going to give me this. So if I divide each one of these by 5, so 5 divided by 5 is 1. So I need a way to turn my 1 into a 1. 20 divided by 5. We should do this the other way around. Sorry, that wasn't very good of me. 20 divided by 5, 45 divided by 5, 80 divided by 5. So if I do 20 divided by 5, that gives me 4. So I need a way to turn my 2 into a 4. 45 divided by 5 is 9. So I need a way to turn my 3 into a 9. And 80 divided by 5 is 16. So I need to figure out a way to turn my 4 into a 16. Well, I have to have the same thing every single time. Same rule. So 0 divided by 5 is 0. So I need a way to keep my 0 a 0. So I need to go from a 1 to a 1, a 2 to a 4, a 3 to a 9, and a 4 to a 16. So I can see again that these are all perfect squares. So I'm going to take that x value and square it, and then multiply it by 5 to get my output. So on 14, again, there's not really any pattern. Each one of these is changing. It's adding by 4 every time. So I'm adding 4 to each one of these. So 1 plus 4 is 5, 5 plus 4 is 9, 9 plus 13 is, or 9 plus 4 is 13, 13 plus 4 is 17. But what I need is a way to get from my input to my output. So just adding 1 is not going to work. It'll work for the first row, but it won't work for all of the rows. So one of the things that I can think of is try to multiply each one of these by a number. Well, if I multiply this times 5, 0 times 5 is not 1. 1 times 5 is 5, so that's not going to work for everything. So it kind of looks to me like we're gonna have to add 1 every time to get our new output. So what happens if we subtract a 1? So 5 minus 1, 5 minus 1 is 4, 9 minus 1 is 8, 13 minus 1 is 12, 17 minus 1 is 16. So 1 minus 1 is 0. So I need a way to turn my 1 into a 4. I need a way to turn my 2 into an 8, my 3 into a 12, and my 4 into a 16. So it looks to me like if I multiply each one of these by 4 and then add a 1, it will give me this output. So I can do y is equal to 4x plus 1. And if you just take each one of your inputs and plug them in here, you should get each one of these outputs. Now on 15, it's a little bit different. So what you need to think about is comparing the outputs from table O and table P with the output from table Q. So compare these two outputs here to this output right here. So what one of the students noticed today was that if we add the outputs from these two tables, it gives us the output for this table. So each one of these equations represents these outputs. So if we're adding these two outputs together to get this output, what would we need to do with these equations to get the equation for this one? So basically what we're saying is that we're just adding the two equations together to get this right here. And if you were to plug in all of these, 5 times 0 squared is 0, so 5 times 0 is 0, 4 times 0 is 0, 0 plus 1 is 1. And if we did the same thing here, 1 squared is 1, 5 times 1 is 5, 4 times 1 is 4, so 5 plus 4 plus 1, 5 plus 4 is 9, 9 plus 1 is 10, and you could do that for the whole table. This function will work for an equation for each one of these inputs on that table. All right, so today we're going to be talking about two different kinds of definitions. Basically what we're talking about is two different kinds of equations. So we're going to be able to write recursive and closed form definitions for a table of values. So in this table, there's a couple of different ways that we could write a function for this. So one way is to focus on what we do to the input to get the output. And so if we focus on the input, we can kind of see that, let's see here. If I multiply each one of these inputs by 5 and then add a 3, that will give me my output. So one way of writing our equation would be 5x plus 3. The other way of thinking about it is to look at just the outputs and see what happens to the output. So really what we're saying is the output is 0. Sorry, I'm not going to say first output. I'm going to say the output at 0 is equal to 3. And then you just add 5 every time. Okay? So our first output, the output when x is equal to 0 is 3. And then for every other output, you just have to add 5, because 3 plus 5 is 8. 8 plus 5 is 13. 13 plus 5 is 18. 18 plus 5 is 23. So we're going to skip this little part. We're going to talk about closed form definitions, recursive definitions, and we're going to talk about difference tables. A closed form definition is a definition or an equation or a rule. So these are all words. Equation, function, rule, all of these are good words. That allows you to find any output for any given input. So whatever the input is, we can plug it into that equation or that function or that rule and find the output. A recursive definition is where each output is found using the previous output. So again, we're talking about an equation, a rule, or a function. Okay? So if we come back here, this would be an example of a closed form definition, and this would be an example of a recursive because we're only talking about outputs. We don't really care about the inputs for the recursive, we care about the inputs for the closed form. All right, this triangle right here is not actually a triangle, it's the delta, it's the Greek letter delta. And what delta represents is change, okay? It represents slope, rate of change, all different kinds of things. So in order to write a closed form or a recursive definition, the very first thing that we need to do is we need to make a difference table. And the only difference between a difference table and an input-output table is that the difference table has a delta column with it. So I'm gonna bump back here really quick. This is an input-output table. And in order to change it into a difference table, we just have to figure out what delta is. What's the change in all of the outputs? So the way that we do that, we always leave the space next to the last output blank. Okay, and if you want to put the lines here to show, that's fine. Okay, and then you just subtract your way up. Subtract your way from the bottom to the top. So subtract the bottom two. 23 minus 18 is a positive 5. And then take the next two up. 18 minus 13, positive 5. 13 minus 8, positive 5. 8 minus 3, positive 5. Okay? So really what we're saying is that the slope is constant. Okay? And if your slope is constant, this is a linear function. And with a linear function, we can write a closed form and a recursive definition. So here is the recursive definition for that table that we just did. So we're going to ignore kind of this bottom half here for a second. So I'm going to cover that up so that we don't get distracted. Okay? If we look at this and we look at the table that we just had, so our input and our output, we started at 0 and our output was 3, then 1, 2, 3, 4, and it was 8, 13, 18, and 23. So there's our input-output table. And then we did a difference table. So we started with delta, and we left this one blank, and we had positive 5, positive 5, positive 5, positive 5. Okay? Everything that we need to know to write the recursive definition is in the line that has the input of 0. So this is the one that you're always looking for right here. Mr. Kemp used to call it your happy place. So here is your first output, your output at 0. And so basically what it's saying, just like what we said earlier, that output, if n is equal to 0, here's our output. This is where we're starting. So then for every input or for every output after that, you just have to add 5. So basically you're taking the previous output and you're adding 5 to it. So if I want to know what the output is for 2, I take the output at 1 and I add 5 to it. Well, the output at 1 is 8. So I take 8 and I add 5 to it, and that's going to give me 13, which is the output of 2. So here is a more formal definition for that recursive. So anything that's in green is going to change. Those are the parts that get replaced. And anything that's in red is going to stay exactly the same, and including this piece out here. You have to have this because it's kind of like 2 equations in one. We have to tell what the first output is going to be, and then we have to tell how to get every output after that. All right, so let's look at this. We've got our difference table here. We're going to turn this into, we've got our input-output table. We're going to turn it into a difference table. So remember, the first one next to the bottom one, that's going to stay blank. And then we're just going to subtract our way up. So 11 minus 9 is positive 2. 9 minus 7 is positive 2. 7 minus 5, positive 2. 5 minus 3, positive 2. 3 minus 1, positive 2. Now, Since all of the deltas are constant, that means that we have a linear function. And when we have a linear function, what we can do is write a recursive definition and a closed form definition. So the recursive definition, we have to start with this piece right here. So the function of n is equal to, again, we're only using the output at 0 and the delta at 0. Those are the only two things that we need for both the recursive and for the closed form definition. So the output at 0 is this one right here. So we just say for the function n, our first output is 1 when n is equal to 0. So if our input is 0, our output is 1. That's where we start. So for any input after, or any output after that, we just take the previous output and we add delta to it. So we add delta. And that is for any output or any input that's greater than 0. So again, here's your output at 0, here's your f of 0, here's your delta. Okay? The closed form is simply y equals mx plus b. We just changed it a little bit, so in this it will be y is equal to delta x plus f of 0. So this is f of 0, this is your f of 0 just means your output at 0, or your output when your input is 0. So the delta is this positive 2. We leave the x where it's at, and we see that our output at 0 is 1. So we just add 1. So both of these would be definitions for that difference table.